Hello students, myself Professor Pathakar, and today we are going to learn numerical which is based on condenser. In our previous lectures, we have learned numerical which is based on LMTD method for parallel configuration and counterflow configuration. We have also learned numerical which is based on NTU method for parallel flow configuration and counterflow configuration. But now, today, we are going to learn numerical which is based on condenser. Remember, in our classification of heat exchanger lecture, we have classified heat exchanger according to physical state of fluid. In that classification, there are two types, condenser and evaporator. So today we are going to learn numerical based on condenser, in which the temperature of hot fluid will always remain same at the inlet and the outlet. So here in the figure, you can see that the temperature of hot fluid, inlet temperature is TH1 and outlet temperature is TH2, and both temperature, this TH1 and TH2, both are same. So here TH1 is equal to TH2. But the cold fluid, inlet temperature TC1 and outlet temperature TC2. So here we can see that from the temperature versus area diagram that the temperature of cold fluid will increase as we are moving from inlet to the outlet of the heat exchanger, but temperature of hot fluid remains same, because here hot fluid loses its latent heat and make a phase change, so that the temperature TH1 and TH2 will remain same. So in condenser, condensing fluid, it means our hot fluid which is going to be condensed. So in condenser, condensing fluid remains at constant temperature throughout the exchanger, while the temperature of the colder fluid gradually increase from inlet to outlet, as we can see this from the figure. So for the condenser, theta 1 would be TH1 minus TC1 and theta 2 would be TH2 minus TC2, or we can say that TH1 is equal to TH2 is equal to TH, so that TH minus TC1 and TH minus TC2. So here the hot fluid loss latent heat which is accepted by the cold fluid. So this is the thing which we need to remember while solving the numerical of the condenser. So let's start our question number 1. A steam condenser is transferring 250 kilowatt. Remember, whenever you read a word condenser or condensing in the numerical of heat exchanger, it is based on the condenser. So the only temperature of hot fluid is given, a single temperature of hot fluid is given, so which is our TH1 and TH2. So a steam condenser is transferring 250 kilowatt. So this 250 kilowatt is our Q. So Q is equal to 250 kilowatt of thermal energy at a condensing temperature of 65 degrees Celsius. So this is our condensing temperature, which is our TH1 as well as our TH2. So in our this diagram, the temperature, inlet temperature of hot fluid and outlet temperature of hot fluid TH1 and TH2 will remain same. The cooling water enters the condenser at 20 degrees Celsius, so it is our TC1 with a flow rate of 7500 kg per hour. This is a mass flow rate of cold fluid. So M of C is 7500 kg per hour. We need to convert it into kg per second. So dividing it by 3600, so it would be 2.08 kg per second. Now we need to calculate the log mean temperature difference. It means LMTD if overall heat transfer coefficient for the condenser surface is 1250 watt per meter square degree Celsius. So here the overall heat transfer coefficient means U is given 1250 watt per meter square degree Celsius. What surface area is required to handle this load? So here we need to find out two things. First, LMTD, it means theta m, and second, the area of the heat exchanger. So we know that to find out the LMTD, logarithmic mean temperature difference, we need the value of all the four temperatures. So first we are going to find out the unknown outlet temperature of cold fluid, which is TC2, which is unknown to us. So we know that from the energy balance equation, or we can use directly this equation, Q is equal to MC CPC TC2 minus TC1. In this equation we know the value of Q, which is already given in equation, 250 kilowatt. Mass flow rate of cold fluid, which is also given, 2.08 kg per second. CPC, so our cold fluid is our water, so specific heat of water 4.187 kilojoule per kg Kelvin. Here the unit of Q is kilowatt, so unit of specific heat kilojoule per kg Kelvin. Now this is a temperature difference, so Tc2 is unknown for us and Tc1 is already given as a 20 degrees Celsius. So from this equation we can easily find out the unknown temperature of outlet cold fluid. It means Tc2 48.70 degrees Celsius. Now we know the value of all the four temperatures, so we can find out the LMTD, logarithmic mean temperature difference. Here our theta1 is Th1 minus Tc1, so that 45 degrees Celsius, because 65 minus 20. Theta 2 is Th2 minus Tc2, temperature difference at the outlet of the heat exchanger. So our Th2 is also 65 and Tc2 is 48.70. So the theta 2 would be 16.3 degrees Celsius. Now putting value of this theta 1 and theta 2 in this equation, so we will get theta m LMTD as 28.26 degrees Celsius. Remember, LMTD is a mean temperature difference, so it has a unit, it is a temperature difference, so degrees Celsius, 28.26 degrees Celsius. Now we need to find out the area. So we know the final equation from the heat exchanger analysis, that Q is equal to U8 theta m. We know the value of overall heat transfer coefficient. We have to find out the value of A. Theta m is 28.26 and Q is also given in the question, 250 kilowatt. Now if here in this equation, if we put value of U as 1250, which is in watt per meter square degree Celsius, and Q is in a kilowatt, so we need to convert this 250 kilowatt into watt, so multiplying by 1000. Theta m is already given as we already find out theta m 28.26, so the value of area would be 7.70 meters square. So this is our final answer, theta m and area required to handle this load. Now let's move on to the another question. Water enters the tube of single pass heat exchanger at 20 degrees Celsius, okay, and leaves at 40 degrees Celsius. So from this two value we can say that this would be our Tc1 and this would be our Tc2. So Tc1 is 20 and Tc2 40 degrees Celsius. On shell side, 25 kg per minute, so this is a mass flow rate of steam condenses. So here we read the word condense, so this is numerical based on condenser. So this is mass flow rate of condenser, mass flow rate of steam, which is our hot fluid. So this is mh, which is 25 kg per minute. We need to convert it into kg per second, so converting minute into second, so divide by 60. So now calculate the overall heat transfer coefficient. It means U is unknown for us, and the required flow rate of water is our cold fluid, so we need to calculate m of C, which is unknown to us. And if area of the heat exchanger is 12 meters square, here the area is given, so area would be 12 meters square. The latent of HFG is 2358.7 kilojoule per kg. Here the latent heat is given of the hot fluid, so HFG is given to us. Why HFG is given, we will discuss it later. At 60 degrees Celsius, so this is the temperature of our steam, so which is our Th1, as well as we can say that this is our Th2, because in condenser we know that the temperature of hot fluid remains same. In this case, the steam will lose the heat, its latent heat, and convert into the liquid, so the temperature will remain constant, and the whatever heat loses by the steam will get by our cold fluid, so its temperature will raise from the Tc1 to the Tc2. So it will from 20 degrees Celsius to the 40 degrees Celsius. We know that specific heat of water we can take as a 4.174 kilojoule per kg Kelvin. So to find out value of U, we need to find out value of theta m, because area is already given in question. We also need to find out value of Q, and we need to find out value of theta m. So to find out the value of theta m, we need all the four temperature in question. We know the value of all the four temperature, Th1, Th2, Tc1, Tc2. So by calculating theta 1, which is Th1 minus Tc1, and theta 2, which is Th2 minus Tc2, and by putting this theta 1 and theta 2 in our LMTD equation, we can easily calculate our theta m, which is 28.85 degrees Celsius. Okay. Now we need to calculate Q. To find out Q, in our previous examples we use equation mc cpc Tc2 minus Tc1, or mc mh cph Th1 minus Th2, but here we don't know the value of specific heat cph. We don't know value of cph, We know the value of CPC, but we don't know mass flow rate of cold fluid, so M of C. So we cannot use MHCPH TH1 minus TH2 or MCCPC TC2 minus TC1. So in that case, one more hint is already given in question, that latent heat of the steam is 2358.7 kilojoule per kg. Now by using this value, we can calculate our heat transfer rate Q. How? So Q is equal to, we can write Q is equal to mH mass flow rate of hot fluid into HFG, because what is the unit of mass flow rate? It's kg per second, and HFG latent heat is kilojoule per kg. So kg and this kg will cancel out, so what will remain? Kilojoule per second. It's kilowatt, which is unit of our heat transfer rate. So we know the value of mH mass flow rate of hot fluid, which is 25/60 kg per second, and we know the value of latent heat, which is 2358.7 kilojoule per kg. So by putting this two value, we can easily calculate our heat transfer rate, which is 982.79 kilowatt. So in this type of numerical, in which where there is more than one unknown in MHCPH TH1 minus TH2 or MCCPC TC2 minus TC1, in that case the latent heat would be given to you in question, and you need to calculate heat transfer rate by using this equation, that you need to multiply just mass flow rate into latent heat to get the value of heat transfer rate. Now as you know the value of heat transfer rate Q and also theta m, by using this equation you can easily calculate the unknown U, because area of the heat exchanger is already given in the question, which is 12 meters square. So by putting the value of Q, A and theta m, we can easily get value of unknown overall heat transfer coefficient, which would be 2838.79 watt per meter square degree Celsius. Now after getting value of Q, we can easily find out the mass flow rate of cold fluid by using Q is equal to MCCPC TC2 minus TC1. In this equation we know the specific heat, which is water, so 4.174 kilojoule per kg Kelvin. If you put value of Q in kilowatt, then you need to put the value of specific heat in kilojoule per kg Kelvin. This is our temperature difference. So if plus 273 and here also plus 273, so it doesn't matter if you put in degree Celsius or Kelvin. So this is how you can get the value of mass flow rate of our cold fluid, which is water, 11.77 kg per second. So here this is theta m, U, Q and mass flow rate of cold fluid. Let's take saturated steam at 120 degrees Celsius is condensing on. So here the word is condensing. So this is based on the condenser method. Condensing on the outer tube surface of single pass heat exchanger. So here the temperature of steam, which is our hot fluid, is 120 degrees Celsius. So this is our TH1 as well as TH2. The overall heat transfer coefficient is 1800 watt per meter square Kelvin. So this is our value of U. Determine the surface area. So area is unknown for the heat exchanger, capable of heating 1000 kg per hour of water. So water is our cold fluid. So this is the mass flow rate of water, which is M of C. It is in kg per hour, we need to convert in kg per second. So dividing by 3600. From 20 degree to 90 degrees Celsius, this is our TC1 and TC2. So TC1 20, TC2 90 degrees Celsius. Also calculate the rate of condensation of steam. Here we need to find out rate of condensation. It means this is our flow rate of cold fluid. So rate of condensation of steam means M of S, or we can say that M of H we need to find out. And assume latent heat of steam as 2200 kilojoule per kg. So here again latent heat is given. So some use of latent heat will be in numerical. Let's figure it out. Here if we need to find out area of heat exchanger, we know that we need to use equation Q is equal to UA theta m. So in that equation, first we need to find out value of theta m, logarithmic mean temperature difference, and for finding value of theta m we need values of 4 the temperature. So all 4 temperatures value are already given in question. We know the value of TC1, TC2, TH1 and TH2. So for our first step would be to find out value of theta m. By putting theta 1 and theta 2 in this equation, we can easily calculate value of theta 1 by TH1 minus TC1 and theta 2 by TH2 minus TC2. And by putting this all values in this equation, we can calculate value of theta m. Now, if we know the mass flow rate of cold fluid, the specific heat of cold fluid, because it is water, it would be 4.186 kilojoule per kg Kelvin. And we know the both temperature TC1 and TC2. So by using MCCPC TC2 minus TC1, we can easily calculate value of Q. Now we need to find out condensation rate of steam. So to find out condensation rate of steam, we can use this equation. Q is equal to MS HFG. This is condensation rate of steam into HFG, because the unit would be kg per second. HFG is in kilojoule per kg, so it is kg per second, kilojoule per kg, and this is our kilowatt, so it is also in kilojoule per second. So from this equation we can write that M of S, condensation rate, is equal to Q by HFG. We know the value of Q. HFG is already given in question, so by putting the value of Q and HFG we can find out condensation rate of steam, which would be 0.037 kg per second. Now we need to find out value of area. So we know the equation Q is equal to U A theta m. By putting value of U theta m and Q in this equation, we can easily find out the unknown value of area of heat exchanger, which would be 0.77 meters square. Let's moving to the next question, which is based on shell and tube heat exchanger. We have already discussed this type of heat exchanger in our classification of heat exchanger chapter, that in shell and tube heat exchanger there is arrangement of one shell in which there are number of tubes, and one fluid is flowing through that tubes and another fluid is flowing above the surface of that tubes throughout the shell, and that's how the heat transfer between two fluids takes place. So in that type of heat exchanger, shell and tube heat exchanger, 6 kg per second of oil flows through the shell side. We don't know oil is a hot fluid or cold fluid. Let's figure it out. The oil enters at 105 and leaves at 40 degrees Celsius, so its temperature is going to down, so it is our hot fluid. So this is our TH1 and this is our TH2. So TH1 is 105, TH2 is 40 degrees Celsius, and this mass flow rate of oil, so that mass flow rate of hot fluid, it is mH, 6 kg per second. Water flows in the tubes entering 32 degrees Celsius, so this is our TC1, leaving at 50, this is our TC2. In addition, specific heat of oil CPH is given, and overall heat transfer coefficient U 416 watt per meter square Kelvin is given. Determine number of tubes. If outer diameter of tube is 100 mm, length of each tube is 1.9 meter, and take correction factor as 0.85. So this is a different numerical. So here, to determine the number of tubes, first we need to find out area of heat exchanger. Then we need to find out surface area of one tube by using diameter and length. Then by dividing area of one tube to the dividing this area to the total area of heat exchanger, we can easily find out how many number of tubes required to compensate total area of heat exchanger. So now the question is, what is this correction factor, which is 0.85? We just multiply this correction factor in this equation. This is our heat transfer rate, Q is equal to UA theta m, and this correction factor, as Q is equal to UA theta m is valid for the heat exchanger which is newly designed or which is recently in use, but after some years of use, the efficiency, the effectiveness of heat exchanger is reduced, because continuous flow of so many fluids make corrosion and some another effect to the internal surface of the heat exchanger. So the effectiveness is going to be decreased by this factor because of use of heat exchanger for the long time. So after some time we need to add correction factor to find out heat transfer rate, because heat transfer rate would greatly affected by the lifespan of the heat exchanger. So whenever there is a correction factor is given in the question, we need to multiply that correction factor in this equation, because it directly affects the heat transfer rate. So to find out the area of heat exchanger, our first goal is to find out the area of heat exchanger. So we know that we have only one equation to find out area of heat exchanger by LMTD method, is that Q is equal to UA theta. In that equation, if we need to find out value of A, then we must have value of Q, U and theta m. U is already given in question, so we need to find out value of Q and theta m. So we know that whenever we need to find out value of Q, we need either MH CPH TH1 minus TH2 or MCCPC TC2 minus TC1. Here we don't know the mass flow rate of cold fluid, but we know that MH, CPH, TH1 and TH2. So by using MH, CPH, TH1 minus TH2, we can easily calculate value of Q, which would be 889980 watt. Now we need to find out value of theta m. Here the question is whether to take this configuration as parallel flow or counter flow. So remember, whenever there is a shell and tube type heat exchanger, it is always considered as a counter flow heat exchanger. So for a counter flow heat exchanger, theta 1 would be TH1 minus TC2 and theta 2 would be TH2 minus TC1. So here we know all the temperature or the four values of the temperature TH1, TH2, TC1 and TC2. So putting these values in theta 1 and theta 2, and by putting theta 1 and theta 2 in this equation, we can easily calculate LMTD for our shell and tube heat exchanger, which would be 24.37 degrees Celsius. Now by putting value of theta m, q, u and correction factor in this equation, we can easily calculate the total area required to get heat transfer rate 889980 watt. It is 103.27 meters square. So the total area required to get this heat transfer rate is 103.27 meters square. So now the question is, how many tubes are required to compensate this area which would give this amount of heat transfer rate? So for that we need to calculate area of one tube. So a tube is a circular and surface area is playing role in heat transfer in shell and tube heat exchanger. So area of single tube, we can say that 2 pi r and its length, because we need to calculate surface area of one tube. So surface area of one tube, it's 2 pi r into L, or we can say that pi dl. The diameter is given and length is given. So surface area of one tube is 0.59 meters square. So how many tubes of this area are required to compensate total area of heat exchanger? So we can calculate by simple dividing 0.59 dividing 103.27 by 0.59. So it says 176 tubes are required to get this much surface area of the heat exchanger to get this much of heat transfer rate. So this is for today's session. I hope you understand all the equations, all the numericals. So in heat exchanger, we first learn numerical, which is based on LMTD parallel flow, then LMTD counter flow, NTU parallel flow, NTU counter flow, and this is our last type of numerical, which is based on condenser and shell and tube heat exchanger. That's it for the numerical of heat exchanger. Thank you so much.